Hi, it's Mr. Bennett here, and today's video we're going to be looking at nuclear instability. Alright, so generally inside an atom there are two different types of forces occurring. So there's a thing called a nuclear force or a strong nuclear force, and that's a force between the nucleons. And what we find is protons, neutrons are treated the same. We call them nucleons, and they will be attractive, or they have a strong bonding together over a very short range. The electrostatic force, which is a coulombic force, which we'll talk about in the second part of the year. All right, so we know that like charges repel each other. Okay, it's a fundamental thing, a little bit like a magnet. So north poles will repel. Well, in electrostatics, well, we know like charges repel each other. So the electrostatic force means that what we'd like to do is we'd like to have these things repel each other. So I've got a little diagram here down below, and we'll just show you what that actually happens. So this particular thing here, over a very short range, this strong nuclear force is in fact stronger than the coulombic force. All right? So that particular strong nuclear force is in fact stronger than the electrostatic force that's going to pull the atom apart. Now what happens here, when we start looking at this scenario over here, when the atoms become really big, then what actually happens is the electrostatic forces now start to overcome the nuclear force. And then we get our decay basically occurring. So the atom basically becomes elongated and then splits into smaller nuclei. All right, so that's the key thing there, I suppose, when we're looking at that. All right, so the different types of decay that we're going to have are the following. All right, so we're going to have beta minus decay, which is an electron being produced. We have beta plus decay, which is going to be a positron being produced. And when we're over a magical number, and the magical number is in fact 83. Elements which have an atomic mass or atomic number of 83 or more become quite unstable. Now, this particular line here, which is an interesting line on this particular graph, that line going through there, that is the number of neutrons to protons. All right, so showing you as we particular get to larger nuclei, then the number of protons of the number of neutrons will increase markedly, all right, over a period of time. All right, so these are the different types of decay. So depending on what the atomic number is, the number of protons and neutrons, as to what type of decay is going to occur. There are three different types of decay that we're going to be looking at. The first one is an alpha decay, and what we're producing there when we do an alpha decay is we're producing a helium. Okay, so it's a helium nuclei. So we're breaking those into two smaller nuclei, okay, and one of them being a helium. I'll get a little demonstration to show you how that works. All right, so if I reset this, and we'll look at polonium being decaying down to lead. A couple of things I want you to notice there is that it's a random process. Okay, it's a random process. So because it just doesn't happen that all of them will go all at the same time. All right, it's a real potluck scenario over here. All right, and so generally what we'll do is we'll have a half-life for a particular type of element with that. The second type of decay is a beta minus decay, and notice here what we're producing in this scenario here is in fact an electron. Producing an electron there, and this one over here is a beta plus decay, and that is producing a positron. Okay, and we'll talk about how that's used in a PET scan and so on. So those are the three different types of decays. A couple of things that you need to note with that. In all cases, we'll get gamma radiation. That's the symbol for gamma radiation, is produced as the nuclei fall back to less excited states. So in all cases, the momentum, mass number and atomic number are conserved. So we have to have conservation of everything in physics. It's one of those things. And another important fact, I suppose, is there is a thing called a neutrino, and that was discovered in 1950. And that was observed from a nuclear reactor in a photosensitive tank buried deep underground. Now, the hard thing about, I suppose, the neutrino, doesn't have a rest mass, doesn't have a charge. It was really, really hard to detect. It took to 1950 for them to do that. And the reason why they knew it existed is because there wasn't quite conservation of momentum and energy. All right, so they knew that there must be another particle in terms of that. All right, so that's in a nutshell how nuclear instability, all right, actually occurs, and this is why things decay. And when we're coming down here, I've got a couple of questions for you to have a go at. What type of decay would you expect under the following scenarios? Have a go at those and we'll review those in class.